Okay, I'm going to walk you guys through a PowerPoint on uniform acceleration formulas. You should have the note sheet in front of you if you're viewing this in class. So I'm going to go ahead and start and walk through these slides. So remember that for the investigation that we've been doing, or been working on the last couple of days, when we plot position versus time, when we have acceleration, we see some form of a parabolic or a squared relationship plot. Okay. One thing that we've been talking about the last couple of days is if we wanted to interpret the velocity in this graph, remember that if I picked some points of interest along this graph, if I wanted to analyze the velocity, I would want to make a tangent line over those points. And if I could find the slope of those tangent lines, I could find the instantaneous velocity at each of those given points. So if you go through and do that sort of analysis and then plot your velocity values as time goes on, and this is something that Logger Pro did automatically for you, and you go in and put those velocity versus time data points into a graph, we see that linear relationship that we got in the lab investigation. So again, the way we would interpret this is the graph starts at 0 because for our lab investigation anyway, the cart started from rest with a velocity of 0 and it steadily increased over time. And of course we've noted the linear relationship here, so we know that if we want to make a model or an equation for this type of graph, it's going to be in y equals mx plus b form. Erase that. Okay, so if we want to develop our model, and we've already done this, but this is a review, we know that our general equation is going to look something like velocity equals slope times time plus an intercept, right? And we identify that intercept value as the initial velocity. So boiling that down to symbols, the slope, because it's rise over run, or change in y over change in x, what we're really plotting here on the y-axis is v, velocity, time on the x-axis. So our slope can really be represented as delta v over delta t. Of course, that gets multiplied by the time value, and again we add in our intercept, which we'll call v subscript 0, just meaning the velocity at time 0. Okay, so when you guys presented your results in class, we identified that the slope of such a graph, or delta v over delta t, is actually the acceleration. Okay, and we use little a as our symbol for acceleration. So again, in short form, the model for this velocity versus time graph is v equals at plus v0. So again, how we would use this equation, if I wanted to know the velocity of this object at any time, as long as I know the acceleration and the starting velocity, I just plug in the time into this equation, and that would calculate my velocity at the time of interest. Okay, so let's look at a slightly more complicated case where the initial velocity is not 0. So in this graph, notice that the graph does not start at 0. This would indicate that at time 0, the object is already moving. It has some positive velocity, which it will speed up from as time progresses. So one thing we need to remember, thinking back to constant velocity, when we were looking at constant velocity, our plots were always horizontal lines because the velocity was steady. And one of the key things that we realized was if we block off a segment of that graph and find the area here, that area equals displacement or change in position. We're going to use that same fact with this graph to do a little analysis of what's going on here with displacement. Okay, so I just mentioned it, but on your notes, we recall that the displacement of the object between time 0 and some time t, shown here, would be the area between the line that is plotted, this plot, and the time axis down here. We would want to bound our area by 0 and t, which is kind of our time interval of interest. So I bound that area and shade it. If I can find the area of that shaded region, I've also found the displacement. Okay, so working through that, you might think, well, how am I going to find the area there? I've got another squiggle here to erase, sorry. How would I find that area? Well, probably the simplest way, unless you remember the formula for a trapezoid off the top of your head, is to divide it up into a rectangle and a triangle. Okay, so area 1 and area 2, we'll just call the rectangle area 1 for simplicity, and the triangle is area 2. So if we have a way to represent those areas, we can add them up to get the total area, which represents the displacement. So area 1, this is simple, right? It's just length times width because it's a rectangle. So if we think about the variables we're using here in this kind of generalized graph, the length, if we want to call the short side the length, has a height or a length of v0. All right, this rectangle is v0 high, in other words. Its width would be the time interval of interest because we're going from 0 to time t. So that's not too difficult. Just two values that are controlling the area of that part of the graph. Looking at area 2, we've got a triangle, right? So remember from your geometry class that the area of a triangle is 1/2 the base times the height. The base would be this side, okay, of the triangle. And notice that the length of that side is from 0 to t, or just simply t. The height is a little bit trickier to analyze. I'm going to suggest that the height could be represented by delta v. Okay? The reason for that is I'm looking at this side of the triangle as its height. Okay? And graphically what we're seeing is, well, that would be the difference from v0 to whatever this final velocity is that we end up with at time t. Okay? So the height from v0 to vf can be represented as delta v. Okay, so we're representing that area in terms of things that we have here in the graph. Okay, so we're going to take a little side note here and make some substitutions and then come back and put these two areas together. So one thing to remember about acceleration. We've defined acceleration as the slope of this graph, right? Change in velocity over change in time. Rise over run. Rearranging that just with some algebra, delta v equals a times delta t, right? If I multiply delta t, both sides of this equation here by delta t, I can cancel. Here. And then, of course, I'd have to multiply this side of the equation by delta t also. So this delta v here, another way to represent it in terms of acceleration would be the acceleration multiplied by delta t, our change in time. And because for this particular graph, delta t starts at time 0 up to time t, delta t, the width of the graph here, is simply t. So I can make a substitution. Because delta v is equivalent to the acceleration times whatever time I'm dealing with here, I can plug that in. So we'll see what happens when we do that. We still have 1/2, we still have t, and we make our substitution. We've got a times t, acceleration times time. So we have some like terms we can group. So we have 1/2 times a times t squared, right? Because we have t times t. So keep in mind what we've done. We've gone through all of this algebra and geometry to represent this area of this graph kind of in a very simple form, 1/2 at squared. And we already saw that the rectangular area has an area of v0 times t. Okay, so if we want to get the total area under that plot, that total shaded area, we need to add up the individual areas of each of these parts, right? Area 1 and area 2. Now the way you usually see that written is like this, okay? 1/2 at squared plus v0t. That quantity represents the displacement that would occur between time t at a given acceleration and a given velocity, starting velocity, I should say. So we've worked through all that geometry to come up with a relatively simple equation that represents displacement. So we could use this equation to do that. If I knew the acceleration of an object and I knew the velocity it was starting with, just by plugging in t here and t here, I could figure out how much position change occurs in that interval of time. So that's in terms of displacement. Sometimes it's useful to translate this into a position versus time model. So when we're talking about displacement, we're really talking about some change in position, some final position x minus some initial position. So if we substitute that in to get one more equation, and we're almost done, keep in mind that if I want to put it in terms of position, if I add x subscript 0 to both sides of this equation, I end up with this. Okay, and this is a really useful equation as well, because now I can predict the position of an object given a certain time, acceleration, initial velocity, and initial position. So this equation is another way to represent those parabolic position versus time graphs that we saw in the investigation. Okay, this sort of equation, when plotted, will give you this sort of shape. And you might ask, well, why didn't we see a term in your investigations? Why didn't we see a t term, you know, a coefficient times t? And the reason for that is, think about what the initial velocity was in the lab that we did. The initial velocity, right, if I did a tangent line there at time 0, was 0. So this term ends up dropping out. So that's kind of the usefulness of this equation, or I guess the application. You might not see all of these terms, okay? You might, in fact, just see 2 of the 3, or even just 1 of the 3, depending on what your values are. What I mean by that, if the initial velocity is 0, this term disappears. If the initial position is 0, this term disappears. If the acceleration is 0, this term disappears. Okay, so you may have a case of constant velocity. If you think back to what those plots look like, if you plot position versus time graphs for constant velocity, remember that those were always linear, okay? Something like that. Because that graph is linear, or one way we could prove kind of that that graph is linear, is the acceleration under that sort of case in position versus time is 0, okay? So if that part of the equation drops away, we end up with a slope times a time plus a starting position, which is what our equations look like prior to adding in this case of acceleration. So this is a very versatile equation. It can represent position versus time in lots of different cases, not just acceleration. Okay, hopefully that made sense. This is posted on Edmodo, so if you need to view it again, you can. We'll apply some of this next week as well. So let me know if you have questions. You can submit those via Edmodo, and have a great day.